Welcome to the first day of the Nexperia Power Live event and welcome to our studio.
My name is Robbie Fernandez, Global Head of Marketing at Nexperia.
And my name is Petra Beekmans and I'm the Global Head of Communications at Nexperia. And we are very excited to be hosting 3 days with great presentations and content. So let's get started with our industrial channel.
Here, live with you, are Siva and Richard to share with you design insights into the benefits of QRR and VSD and the use of 80 to 100 volt MOSFETs in switching applications. The session will be about 25 minutes long. We will start with the presentation and then questions. Questions are anonymous. You can ask your question using the question pane on the right-hand side of your screen. Please ask your questions to our experts or share your own experience and insights. And with that, I will hand over to Siva and Richard to begin. Gentlemen, the floor is yours.
Thanks, Robin. Thanks, Petra. Good morning and good afternoon to everyone. Welcome to Nexperia's Power Live event. I'm Shiva Uppaluri. I'm an International Product and Marketing Manager for BGMOS. Today, I'm here with my colleague, Richard Daly. He's our Power Applications Engineer. In this session, we will discuss the importance of MOSFET's body diode and the benefits of low QRR and VF in some of the applications out there. A body diode occurs in all MOSFETs at the junction between the PN doped silicon and essentially it is a body diode that's formed between the P-type body and the N-type drain region. This unavoidable part of the MOSFET structure, yet an essential part, is important for the MOSFET behavior itself. Designers exploit the body diode in various applications, including synchronous and freewheeling applications. This body diode allows inductive currents to circulate without creating voltage spikes. So great stuff. It will help the designers in every possible way, but there is no such thing like a free lunch. Like any other diode, there are limitations and losses associated with the body diode. And the most commonly understood losses is the conduction losses. And the conduction losses are caused by the forward voltage drop of the body diode when current flows through it. And the switching side of things are caused by a parameter called reverse recovery charge. So this is the charge that's trapped in the PN junction when the body diode conducts enough current through it. Let's go into the details of how these two parameters will impact certain applications. Here you're seeing a typical application, which is a synchronous buck converter. As you can see, during the dead time of the synchronous buck converter, it's the body diode of the MOSFET that is tasked to conduct the freewheeling current from the inductor. As this current flows through the body diode, it results in the accumulation of the charge that I was referring to in my last slide, which is the reverse recovery charge. The issue with the reverse recovery charge is when a body diode is reverse biased, you expect it to stop conducting instantly, but it won't happen as long as the reverse recovery charge that is trapped in the PN junction is removed from the body diode. And this charge is removed in the form of a spike current, which is referred in the MOSFET datasheets as reverse recovery current. So when the high side MOSFET comes on at the start of the next cycle, instead of the body diode blocking straight away, it will need to flush out the stored charge before the cycle is set. And this stored current is removed in the form of a spike current, which obviously results in I²R losses in the high side MOSFET and other components in the circuit. Not only that it results in I²R losses, but these current peaks with fast rising and falling edges interacts with the parasitic inductances in the PCB and the MOSFET lead frame itself, which results in voltage spiking. And the voltage spike can affect the MOSFET's performance from anywhere from deteriorating its operational ability over the lifetime to instantly killing it. So let's go to the next slide. So over here, what we did is we ran a simulation using our PSMN 6R900 YSF. We created two models. One is an accurate representation of the device itself. Another one is with an inflated QRR. We set the QRR to be 2 times its natural QRR to study the impact of QRR in the application. As you can see, the device with the low QRR not only has a smaller reverse recovery current peak, but it also has less ringing following the instance. And also, if you focus on this area of this graph here, the device with higher QRR resulted in additional energy losses. All these things are not good for your application. And one other area where we would like to bring your attention to is the TA by TB ratio, what we refer to it as the softness ratio, that also is improved by reducing the QRR of the device compared to the one with 2 times the QRR. So the effects of QRR are profound, and hence it is important we take QRR into consideration while designing MOSFETs into your application. Further going into the details of what we saw in the last slide focuses on the peak current and the ringing following that, but this peak current or these current peaks in general interacts with the parasitics, as I mentioned, and that results in higher voltage spikes as well. As you can see, the MOSFET with lower QRR resulted in a 48.6 volt spike compared to the one with higher QRR that resulted in a 52.4 volt spike. To put this in practical application context, if you are working with a MOSFET, let's say it's rated to 60 volt, to see a peak coming closer to its breakdown voltage often forces the designers to choose a much higher voltage MOSFET than necessary for the application. By tuning the QRR and by choosing the right MOSFET for the application, you can use a smaller rated MOSFET, which in turn results in lower RDS on and lower costs. So QRR indeed is an important parameter to look at while choosing your MOSFET. So we thoroughly covered the impact of switching losses in the applications. Now coming to the most commonly understood loss, which is the conduction losses. We created 2 scenarios here. In scenario 1, which is an ideal case scenario really, it's a scenario where there is a 0 dead time and the MOSFET is doing synchronous conduction throughout its operational cycle. So the typical RDS on of a MOSFET in this case is 4 milliohms, and it's conducting 20 amps for 18 nanoseconds. So the I square R losses associated with such a conduction event is about 1.6 watts. In other words, it's 128 nanojoules of energy. However, this is not a practical scenario. In real life applications, designers design in certain dead time, which is the time where both the high side and the low side MOSFETs are turned on at the same time, allowing for the body diode to conduct in this dead time period. When the body diode starts conducting, that's when the VF or the forward voltage drop of the body diode plays a significant role on how the conduction losses looks like during this dead time interval. As you can see here, if we choose a MOSFET which has 1.2 volts forward voltage drop at 20 amps of conduction current, it resulted in 24 watts of energy power losses. If you reduce the voltage drop of the body diode from 1.2 to 1, it straight away decreased the power losses from 24 to 20 watts. 4 watts is a lot of power to be saved. It has a significant impact on how you design your thermals around the MOSFET, and also it helps maintain a lower temperature while the MOSFET is operating under these conditions. And the diode energy losses are down at 1,920 nanojoules or 1.9 microjoules. And just to put it into context, if it is possible to minimize the dead time and make the MOSFET conduct for as long as you possibly can, or your design permits, the energy losses can be limited to about 128 nanojoules. And if you bring the body diode to conduct for the same amount of time, the energy losses are almost 12 to 15 times higher. Hence, it is important the design of these circuits with limited dead time will have a much better impact on our overall circuit performance. Nevertheless, given the limitations on how much small the dead time can be, it is important to choose a MOSFET that has a lower VF compared to what you can get elsewhere. And moving on from here, I'll hand over to my colleague, Richard Daly. He will talk through some of the benchmarking that we did using our NextPower 80 and 100 volt devices. Richard?
Yep, so thank you very much, Siva. What we've done is we took our range and portfolio of our 80 volt and 100 volt products, and we really wanted to make it a fair comparison between our product and what's the competitor product on the market. Now, there's many topologies that we could use, but we really wanted to look at the performance of the MOSFETs in an application. So we made it very simple. We did a buck converter, which is a 48 volt to 12 volt. So adding minimal additional components, so it's not giving an unbiased result. We've been using the same MOSFETs for the high side and the low side for the testing, keeping a fixed inductor, a gate resistor of 0 ohms to actually see the benefits of the product, and keeping the fixed dead time. We're going to be running this test in a CCM mode, and we're going to be doing some sweeps from 2 to 20 amps. The key areas that we're going to be looking at is switch node spiking, efficiency versus low current, and efficiency versus switching frequency. Now, just to reiterate in terms of how we've done the testing, if an example is if we have a 3.9 milliohm product, we took the relevant competitor parts, that may be a 3.9 or it might be a 4 milliohm, grouping them together, doing the test on the same day, on the same bench, and on the same setup, just so that it's not biased at all. So let's look and dive into the results. The first one we're going to be looking at is efficiency versus load. What we can see here is that we've got the resistance of our products and the competitor equivalents across the x-axis, and on the y-axis is what is the efficiency that we recorded during the testing. But we've also looked at frequency. We've been sweeping the frequency from 100 kilohertz to 500 kilohertz. And what we've noticed is that the Nexperia products have been finely tuned to have efficiency either comparable or slightly better than some of the competition on the market. And as you can see, as we go up in RDS on, our products at higher loads become actually first or best in class. But it's all good having high efficiency at high load, right? Your design might not need high loads. So let's dive into average efficiency and see what the average efficiency across various loads from 2 to 20 amps. So Siva, could we go to the next slide? Thank you. So same thing again. We have the RDS on of our portfolio across the bottom with the equivalent competitor parts. And what the average efficiency is showing us now is actually we've got very comparable efficiency across the range. We are still maybe first, second, or even third in some cases on the product, but the difference between this is less than 1%, and in some circumstances less than 0.5%. So when you come to selecting a product or a part, there's not much in it. But what the key benefits of the Nexperia Power 100 and 80 volt products are is a switch node spiking. And this is what we did some testing on. This testing is we're going to actually show you what the benefits are, and this is because of this low QRR. So let's dive into the spiking. So spiking, we have the best on the market, and this is purely down to us fine-tuning the products for the right application, lowering QRR, balancing with COSS. What we can see is from 100 to 500 kilohertz across the range is that we have got the best in class. And what this really tells us is what does it help with spiking? Well, low QR body diode helps reduce EMI emissions, and the EMI emissions are critical when doing EMC testing and compliances. So we'll dive a little bit more into EMI a little bit later on. We've been talking about the 100 volt products here. We also have the 80 volt products, and what we've done is we've benchmarked our 80 volt with our 100 to see what the benefits and performances of them products. So next slide, please, Siva. So what we've done is we've compared our 80 volt product with our 100 volt product with a similar spec RDS on. And what we can see is that from efficiency at load, average efficiency, and switch node spiking, there is hardly any difference at all. So if you think that your product may not need a 100 volt product, You can still choose an 80-volt product, which has exactly the same benefits: high efficiency and lower spiking. But what I want to dive into a little bit more is about that EMI. The EMI is critical when doing some EMT testing. So let's jump to the next slide. What we've done is we've took our 5.6 milliohm product, an equivalent competitor part, we've run a frequency sweep. And the lower QRR is enabled us to deliver around 10 decibels lower EMI emissions between the 80 to 150 megahertz. This is a real benefit when coming to EMT testing. So without that, I'm going to hand over to Siva, which will tell you a little bit more about the portfolio and the benefits that we've been discussing of the body diode and the QRR.
Thanks, Richard. As Richard summarized, the QRR is a critical parameter in many ways for switching applications. And NextPower 80 and 100-volt technologies brings the benefits of those QRR while keeping the RDS zone competitive. So in this slide, I'll discuss some of the features and the associated benefits that we bring to the equation. The low RDS zone of 3.5 milliohms at 80 volts and 4.3 milliohms at 100 volts in our LFPAC56 results in lower I²R losses, and it also allows for us to rate a high ID max ratings, which is mostly down to the package that we choose, that is the LFPAC56E. And we also offer a very low QRR. As you can see from the graph over here, it's about 60 to 70% lower than leading competitors. And as Richard explained in his benchmarking, this not only results in increased gains, but it also results in low spiking and low ringing and eventually a better EMI profile. Optimized body diode, we paid special attention to bringing that VSD value to a minimum. But what it leads to is during the dead time, it minimizes those conduction losses, especially in synchronous rectification and freewheeling applications. Just like with any of our Nexperia's portfolio, we offer strong avalanche rating, which is 100% tested at a very high current of 50 amps. And this results in rugged and reliable switching. We optimize the output capacitance. This further contributes to keeping the spiking to a minimum while resulting in high efficiency. And the NextPower 80 and 100 volt portfolio is rated to 175 degrees. What this allows us to is to meet the IPC 9592 standard for telecom and computing applications. And our LFPAC, as you are all probably familiar by this point, is wave solderable, which keeps the manufacturing cost to a low, and especially in the space-constrained PCB assembly applications. Now, the typical applications that we are targeting with this portfolio are AC-DC synchronous rectifier applications, DC-DC primary side and secondary side switching, especially in the 4G and 5G telecom space, and BLDC motor control, of course, and the LED lighting. With this, I would like to conclude our session. And before I go away, in this slide, we summarize the design-in resources, which we sincerely hope will help some of the designers out there in their design-in process. Now, we are open for any questions or if there are any insights that you would like to share.
All right. Thank you very much, gentlemen. Great first session. Let's see if we have some questions coming in from the audience. I see here the first question already coming in. How does QRR affect EMI emissions?
Siva, do you want me to just take this one?
Sure,
Okay.
Richard, go for it. Yes.
Yeah. So with fast transition currents, so an example IRR, they flow for tens of nanoseconds through the traces of the PCB. And these act as like 10 antennas and create an RF in the range of 100 megahertz. This can help reduce IRR and can reduce EMI in its actual range. So having lower QRR really does help with EMI. Would you like to elaborate any more, Steve, or is that all?
No, Richard, you comprehensively covered it. I might bring audience attention to this part. So as we demonstrated here, especially in the 80 to 150 megahertz range, we managed to keep the noise 10 decibels points lower compared to some of our competitor types.
All right. Thank you guys for that answer. Next question here. Would the same product work in a flyback configuration?
Richard, you want to take that?
Yeah, I'll take that one. So yes, answer is yes, it would. But what I wanted to put the focus on was there is many topologies out there, and people use the MOSFETs in different configurations. The reason we chose the buck regulator is just to really focus on the dynamics of the MOSFETs. As you go into different topologies, you've got more extra components added to the system, adds more complexity. The main purpose of this is to look at the switching characteristics, how the efficiency is being produced from our products, and looking at how our products can help reduce EMI through our low QRR and our spiking.
Yeah, if I may add to that, Richard, as Richard pointed out, we chose a synchronous buck converter as an example to demonstrate what benefits you can get by choosing a MOSFET that is tuned for low QRR. But again, as Richard pointed out, these MOSFETs excel in all sorts of topologies. In any scenario where you are doing hard switching, especially, QRR becomes extremely critical. And those are all the applications where the NextPower portfolio will definitely shine.
All right. Thank you guys for that answer. Just for the people at home, you can enter your questions in the question pane on the right-hand side of your screen. I see we have another one coming in here. Does QRR depend on the MOSFET current?
I will take that question, Richard. Yes. Short answer is yes, it does depend on the current. And we do quote our QRR values at the current that we measured or characterized the devices. The general tendency of the QRR is the larger the forward current that the body diode is subjected to, the larger the QRR value tends to be. But for apple-to-apple comparison, as long as we are comparing our devices with the competitors under the same conditions, you will get a clear picture on how much improvement you can get using the Nexperia's devices.
Okay, great. Sorry, do you have time for one more question? All right, last question then for you guys. Can NextPower 12 milliohm to 15 milliohm really replace competitor parts with lower artisan, like 7 to 10 milliohm?
Richard?
Yeah, I'll take this one. Yeah, so in the buck regulator application that we've tested, what we do see is that the 12 to 50 million from our portfolio can be replaced with a 7 to 10 million. This is purely down to the low dynamic losses, which helps to offset the high RDS on. Customers really should grab some samples, test them in your own applications, see how it performs. And if you're stuck, just send an email into us and we'll help you out with your application and help you select your MOSFET, which is best suited for your application. If you wanted to reduce the efficiency a little bit, but you need to increase it on reduce your spiking, by all means, drop a question in. We can try and help you out.
Great. So thanks a lot. So that brings us to the end of this live session. Thank you to Siva and Richard. And if you want to know more about MOSFETs, you can follow the resource links underneath the screen or chat live to one of the power experts. And you can also watch Richard present actually these products in action in the on-demand section.
Please stay around. Our next live session on managing inrush current and hot SOA curves when designing with power MOSFETs will start after a short break.